Okay, so back to fluid friction for just a couple of other minutes. So what we said was it's dependent upon the speed the object's moving, it depends upon the shape of the object, and it depends upon the surface area of the object. Okay? That's why cars are designed the way they are and don't have square fronts. Because if they had square fronts, they'd catch a lot of friction, right? Fluids are liquids and gases. So we have fluid friction when something's moving through air or moving through water. The bigger the speed, the bigger the fluid friction. So the fastest runners, the fastest swimmers, the fastest bikers are affected most by fluid friction. The slow guys don't encounter it as much, but the fast guys do. That's why the swimmer Michael Phelps, remember him, the American swimmer that broke all those records? One of the reasons he broke it is because he had this amazing swimsuit that was made out of like shark, the same, manufactured shark skin. So there was very little fluid friction. After that Olympics, they banned that swimsuit because it was like a wetsuit. It was so expensive that other people couldn't afford it, and it gave him an unfair advantage. But his reasoning was he was the fastest, so he was experiencing more fluid friction, so he needed it. Okay, but it's also why like bikers and swimmers and runners wear really skin-tight clothing, shave every hair that you could possibly see on their body. They don't want any extra surface area to get more fluid friction in it. Okay, this is also where terminal velocity comes from. Like when you first drop an object, it doesn't have any velocity, so the only force acting on it is gravity. But as it speeds up going down, the force of gravity stays the same, but the fluid friction will begin to get bigger, right? So the faster and faster it goes as it falls, the bigger and bigger the fluid friction will get, until you will hit a point where the fluid friction will equal the force of gravity acting on it. And when you hit that point, there's no net force in the y direction. And so it now means that this object will fall at a constant velocity, right, if there's no net force. And that's what we call terminal velocity. It doesn't necessarily mean that if you fall at that force, it'll be terminal. It means final. Like that's the biggest velocity you can get to. And it's not a one-size-fits-all velocity. It depends on, am I dropping the pen, my water bottle, or a random student, right? If you drop a penny, it's going to take longer to reach terminal velocity than if I drop a sheet of paper, okay? Because they have different surface areas, different shapes, and therefore there'll be a different amount of friction acting up. Because fluid friction depends on these three things, it does not obey the equation FFR equals mu Fn. It is not fun. And so the only way we'll be able to calculate fluid friction in this course is by doing like the sum of the forces on an object, and if we know the other forces, we can find fluid friction. We can't use the mu Fn. If we wanted to find its own equation, it would change depending upon the shape of the object and the speed of the object and the surface area. You would need calculus to do this, and you don't have calculus yet. And so this one waits for university. So it will come in and we can include it. Like I could tell you the fluid friction acting on an object is 42 newtons, and you could include it in the sum of the forces, but you wouldn't be able to calculate it with an equation like FFR equals mu Fn, if that makes sense. Okay, so that's a brief review of the three forces that we're going to encounter a lot. Of course, there's like the force people are applying. So the next day you're in class, we'll do a couple of reminder examples of these forces, questions, and then you'll get to practice some of them. In the meantime, though, you have this little sheet, displacement and equilibrium forces, and I would like you to do these three questions, okay? We'll go over them tomorrow. We'll do some sum of the forces questions. All shall be great. Thank you.